Today I'll tell you about composition series. Our primary objective is to understand the category of modules over a ring. So let R be any ring, and let's denote by R mod the category of all R modules. We want to understand this category. So in some sense, we want to understand what are all the objects of this category. And one way to understand a category is to try to understand all its objects up to isomorphism. So for example, we may want to know how to classify all R modules up to isomorphism. Now this is usually a tall order. Let's take even the simplest example. Let's take R to be the ring Z, and we know that R modules are the same as abelian groups. The category R mod is isomorphic to the category or AB of abelian groups. How does this work? Well, if you have an R module M, you can just take it to the underlying abelian group. And if you have an abelian group G, you can put the structure of, or maybe I should say Z module here, just to be clear, we're talking only about Z. You can put on G the structure of a Z module. So how do you do it? You need to say, given an integer n and an element G of G, what is n dot G? And you say that n dot G is G plus G plus G plus G taken n times if n is greater than or equal to 0. In particular, if n is equal to 0, then n dot G is 0, the unit of the abelian, the identity element of the abelian group. And if n is negative, then you take it to be minus of minus n dot G. Minus n would then be positive, and so this would make sense by the earlier case if n is less than 0. And so an abelian group becomes a Z module. So the category of Z modules is the same as the category of abelian groups. And in Algebra 1, we have seen a structure theorem for finitely generated abelian groups. So what this does is, this gives a classification of finitely generated R modules up to isomorphism. However, it turns out that if you remove this condition of finitely generated, then the classification is not known in general. We do not know how to classify all Z modules, or we don't know how to classify all abelian groups up to isomorphism. So in fact, in Algebra 1, we looked at the classification of finitely generated R modules. Maybe I should say here again Z. We did the classification of finitely generated R modules for any PID R. And in some sense, that tells us a lot about the category of R modules when R is a PID. So we may take all R modules, but usually that's quite unmanageable. We would take finitely generated R modules. Anyway, I don't want to get into specifics here. I just want to motivate things. So, for example, consider the R module, consider the Z module, Z mod 8Z. So this cannot be written as a product of two abelian groups or a product of two Z modules. So is not a product of two Z modules. So in some sense, it is a building block for the category of Z modules. But on the other hand, it's not the simplest object that you have. This Z mod 8Z contains, for example, 2Z mod 8Z, multiples of 2 inside it, and that in turn contains 4Z mod 8Z. But that is a maximal submodule and there's nothing else. So this kind of breaks up this R module, Z module, into smaller and smaller pieces. And to get an idea of what is happening in between these two pieces, you can compute the quotient of Z mod 8Z by 2Z mod 8Z, and you'll see that here this quotient is isomorphic to Z mod 2Z. Here this quotient is also isomorphic to Z mod 2Z, and here this quotient is also isomorphic to Z mod 2Z. So this is the kind of thing that we are going to be interested in the next couple of lectures. So this Z mod 2Z is an even more fundamental building block. This is what is called a simple Z module. So let's go to the definition of a simple module in general. So firstly, recall that if M is an R module, then a submodule of M is a subset N of M, such that firstly we want that N under addition is a subgroup of M. The underlying abelian group of N is so N has to be a module, of course, and it has to be the underlying additive group has to be a subgroup of the underlying additive group of M. And the second is that it should be stable under all the operators coming from R. In other words, Rn belongs to N for all R in R and for all N in N. In the category of Z modules, submodules are precisely subgroups. Now we can define a simple module. An R module M is said to be simple if it does not admit, well, firstly, if M is not just 0, that is, it's a non-trivial module, and if M does not admit a non-trivial, i.e. a non-zero proper submodule. Okay, so for example, Z mod 2Z is a simple Z module, whereas Z mod 8Z is not a simple Z module because it admits non-trivial proper submodules. Okay, and now we can define the main object of this lecture, namely a composition series. So given an R module M, a composition series for M so this is what we are defining. Composition series is a sequence, a finite sequence we will take. So I goes from 0 to N of submodules of M, such that, well, firstly M0 is equal to M, Mi contains Mi plus 1, and lastly Mn is the trivial module. Okay, so basically it's just a sequence. We have M0 contains M1 contains Mn. There are n plus 1 things, the first one being M and the last one being 0. So that's just the definition of a composition series. Sometimes we'll be requiring a composition series to be strict. So we'll say that mi I0 to n is strict if mi properly contains mi plus 1 for all I. Okay, so we often don't want to be distracted by composition series where terms just repeat, and so we will use strict in that case. And sometimes we want the flexibility of allowing composition series where terms do repeat, in which case we will not insist on strict. Now we can compare composition series. There's a partial order on the set of all composition series, and this partial order is that of refinement. So given two composition series, sigma prime, a composition series sigma prime is said to be a refinement of sigma of a composition series sigma if the terms of sigma can be found among the terms of sigma prime. So for example, if we look at Z mod 8Z, we have a composition series which is just Z mod 8Z contains Z mod, let's say 4Z mod 8Z contains 0, is refined by, so a refinement of this is Z mod 8Z contains 2Z mod 8Z contains 4Z mod 8Z contains 0, because each of the terms of this first series sigma is to be found amongst the terms of the second series sigma prime. So we'll say that sigma prime is a refinement of sigma. Okay, and one last definition related to a composition series. Given a composition series let's say mi, I goes from 0 to n, its quotients are just the R modules qi defined to be mi mod mi plus 1 for I equals 0 up to n minus 1. So these are the quotients of a composition series. So we've already seen some examples. Here, for example, I have written down the quotients of this composition series in red. Okay, so let's just study all these concepts using an example. So example, take R to be Z. So we're just talking about abelian groups, and let's look at M equals Z mod 12Z. So this is an R module. In order to write down the composition series for M, we will first find it helpful to write down all the submodules of M. So let's first list all the submodules of M. I list it somewhat visually so that you can see all the different submodules. So for example, we have okay, so the largest submodule is Z mod 12Z itself. Let me just call it M. And then this contains two submodules, the multiples of 2, which I'll call 2M, and the multiples of 3, which I'll call 3m. It also contains the multiples of 4, which I'll call 4m. But the multiples of 4 are contained inside the multiples of 2. And then there are multiples of 6, which are contained inside multiples of 3. However, multiples of 6 are also contained inside multiples of 2. So this diagram, and then there's the trivial module. So these are all the submodules of M. There are totally 6 of them, including M and the trivial module. And from this, we can write down all the composition series. They're just going to be sequences where you choose modules going down in chains in this diagram. But you don't have to take everything along a chain. So you start with M and you end with 0, and you can take a path going from M to 0 and pick some things along that path. So the smallest composition series that you can have is just a composition series which has 2 terms, that is n is equal to 1. You have M contains 0. So this is a composition series with n equals 1. So let's just, now I'm writing down the composition series of M. And this, every composition series will be a refinement of this most trivial, smallest composition series. And now this composition series will contain a 2-term composition series, or rather maybe I should say 3-term composition series, but n equals 2. So this will contain, one for each non-trivial submodule of M. So you can take M contains 2M contains 0. You can take M contains 4M contains 0. You can take M contains 3M contains 0. And you can take M contains 6M contains 0. So these are the composition series with 3 terms, or n equals 2. And I'll just draw a line to indicate that each of these refines the trivial composition series M contains 0. And now we have the next stage where n is equal to 3. So this composition series M contains 2M contains 0 can be refined by adding a term 4M. So here we have M contains 2M contains 4M contains 0. So this is certainly a refinement of this composition series, but it is also a refinement of this composition series. Okay, now how can we refine M contains 3M contains 0? We can refine it by adding M contains 3M contains 6M contains 0. And this is going to be a refinement of these 2 composition series. But there's one more composition series where you take this diagram and go across from the left to the right. So M contains 2M contains 6M contains 0. And this is going to be a refinement of M contains 2M contains 0 and M contains 6M contains 0. But it's not going to be a refinement of these 2 guys in the middle. And that's it. So this diagram shows you all the composition series of Z mod 12Z, and it also shows you the refinement relations. If you go from up to down along a green line, then you get a refined composition series. And so you see there are 3 composition series which are maximally refined, which cannot be refined any further. Now just for fun, let's also write down the sub-quotients here, the quotients of this. So here we get 2 Z mod 2Z. I'll just write down the size of the sub-quotients. They're all cyclic groups, so there's no ambiguity there. And 2m is like, it's of order 6, so this here is 6. Out here you have 4 and you have 3 as the subquotients. Out here you have sorry, I think this one is, yeah, this one is 3 and 4, and out here you have 2 and 6. So these are the orders of the quotients of these series. And let's continue that down here. So here you get 2, 2, 3. Here you get 2, 3, 2. And here you get 3, 2, 2. So you see, there's a nice pattern also in terms of the subquotients. One thing that you observe here is in all these composition series at the bottom of this diagram, the subquotients are the same, but they appear in different permutations. Okay, so we'll be interested in composition series of this last kind, the most refined ones, the ones that cannot be refined any further. And those are called Jordan-Holder series. So definition, a composition series is called a Jordan-Holder series if it does not admit any refinement. But well, a series technically is a refinement of itself, so I should say any proper refinement. If it does not admit any proper refinement, where by proper I mean a refinement apart from itself. So you must add at least one term. And another way to characterize Jordan-Holder series is in terms of the quotients. So that's a simple lemma that a composition series mi, I goes from 0 to n, is a Jordan-Holder series if and only if all its quotients are simple. Let's see how to prove this. The proof is fairly simple. So suppose, so we have two ways to prove. So suppose one of the quotients is not simple. So suppose, mi mod mi plus 1 is not simple. So what that means is that we have a proper submodule, a non-trivial proper submodule, be a non-trivial proper submodule. Then what you can do is let Q be the quotient map from mi to mi mod mi plus 1. And in here you have m, which is a submodule, and you can look at Q inverse m, which is contained in this. Now, since mi strictly contains, since mi mod mi plus 1 strictly contains m, and that is strictly non-zero, we have that mi strictly contains Q inverse m, and that strictly contains mi plus 1. So now you can write down a strict refinement, which is m0 contains m1 contains and then you take mi, and then you insert this new term q inverse m in between, and then mi plus 1 up to mn is a strict refinement. Which means that the original series was not Jordan-Holder. So that proves one way. It proves that if the series is Jordan-Holder, then every quotient is simple. Now conversely, we will show that if there is a refinement, so if we have a refinement, m0 contains m1 contains mi, and then we have a new guy which we insert, let's call it n contains, and then we go back to our old series. Is a strict refinement. Then what we are saying is that, so I think when I say strict refinement, I need to be a little careful. The terms, there is a term in this series which is not one of the terms in the other series. So what that means is that this n is neither equal to mi nor equal to mi plus 1. So what we have is mi strictly contains n, which strictly contains mi plus 1. Which implies that if you look at mi mod mi plus 1, this strictly contains n mod mi plus 1, and that strictly contains 0, which means that mi mod mi plus 1 is not simple. So this shows that if all the quotients are simple, then you cannot further refine a composition series. Okay, so now in the next lecture, I'll show you that a Jordan-Holder series is essentially unique in a certain sense, and we will prove that theorem. It's called the Jordan-Holder theorem.